All right, let's get right into it. Welcome back to The Explainer. Today, we're unpacking the actual mathematical engine that drives machine learning. You know, we hear all these buzzwords constantly: AI, predictive modeling, neural nets. But beneath the hype, there is this incredibly beautiful, rigorous engine powering the whole thing. And that engine is mathematical optimization. So today, we're going to pop the hood and see exactly how it operates.
So it all really boils down to this one question. How exactly does a machine learn from its mistakes? It's not magic, right? When a machine is learning, what it's actually doing is a rigorous, almost physical exploration of a massive data space. It's constantly adjusting its internal parameters based on continuous mathematical feedback, just getting a little bit better step by step.
To really wrap our heads around this, picture it like this. We are trekking through this rugged, multidimensional mountain range. In machine learning, this terrain is our data. The high peaks, that represents high error, where the model's predictions are just completely off base. The valleys, on the other hand, represent low error, where predictions are highly accurate. So our ultimate goal for this whole expedition is simply to find the absolute lowest point in the deepest valley we can. Okay, let's dive into this. Here is our roadmap for the trek. 1. The optimization engine. 2. The gradient descent journey. 3. The overfitting trap. And 4. Navigating complex terrain. Starting with Section 1, the optimization engine, defining our destination.
Before we take a single step into those data mountains, we need to know exactly what we're looking for at the bottom. Enter the loss function. Think of this as the elevation map for our landscape. In machine learning, this objective function penalizes the mismatch between what our model predicts and what the actual data shows. Finding the best possible model means minimizing this loss function. You want that cost, that elevation, to be as close to zero as humanly or physically possible.
Let's ground this abstract math in a real-world scenario. Imagine you have a matrix of personal attributes, kind of like a giant spreadsheet showing age, education level, years of experience, alongside people's actual salaries, and we want to predict a totally new person's salary. Our loss function here is calculating the square difference between our predicted salaries and the actual known salaries in our training data. By adjusting our model to shrink that squared error, we're effectively walking straight down into that valley of accuracy.
Moving on to Section 2, the gradient descent journey, finding our compass.
So now we know we want to reach the bottom of the valley. But in a thick fog of millions of data points, how do we know which way is down? We need a mathematical compass, and that compass is the gradient. Mathematically speaking, the gradient is a vector made up of partial derivatives. It's basically calculating the slope of our loss function for every single parameter in the model. But there is a huge catch here. The gradient vector always points in the direction of the steepest ascent. It points straight up the mountain. So to get to the valley, our algorithm has to intentionally walk in the exact negative direction of the gradient.
Which brings us to the famous gradient descent algorithm. It's an iterative trick. Step 1, initialize parameters. We essentially drop randomly into the landscape. Step 2, calculate the gradient to find that slope. Step 3, update parameters. We take a step in the opposite direction of the slope. And the size of this step, that's our learning rate. If you take a step that's too small, you'll literally be there forever. But take a step that's too large, and you might accidentally overshoot the valley entirely. Finally, step 4, repeat to convergence. We just loop this over and over until the slope flattens out, meaning we hit the bottom. Now in reality, these data terrains are incredibly rugged. So to build out our mathematical toolkit, we bring in a heavy hitter from calculus, the Taylor expansion. What the Taylor expansion does is allow us to take these wild, chaotic objective functions and approximate them with much simpler, smooth polynomial curves, often quadratics. This localized simplification is a lifesaver because it lets the gradient descent algorithm easily calculate its next step, keeping our compass hyper-accurate even when the terrain gets crazy.
Let's look at Section 3, the overfitting trap, hazards of the wilderness.
Because this landscape is absolutely full of dangers, and sometimes perfecting your current path leads you straight into a trap. The legendary computer scientist Donald Knuth had this fantastic quote. He said, "If you optimize everything, you will always be unhappy." Not only is that just incredibly good life advice, but it is literally the fundamental rule of machine learning optimization. If we just blindly optimize parameters until we perfectly memorize our training data, we are going to be very unhappy when we unleash that model in the real world.
So why does this matter? Well, it highlights the core difference between traditional optimization and machine learning. In traditional optimization, your goal is just to minimize the objective function on the known data. That's it. But in machine learning, we only actually care about how the model performs on unseen test data. If your model perfectly memorizes the specific bumps in the training data valley, but then fails completely on a new landscape, that is what we call overfitting. We literally have to hit the brakes and stop descending before we over-optimize.
And that brings us to Section 4, Navigating Complex Terrain, Advanced Optimization Tactics. In this final stage, let's look at advanced survival tactics. What happens when our standard compass fails? When calculating the gradient for every single variable at the exact same time becomes way too computationally heavy, we switch to coordinate descent. Instead of trying to move diagonally across a multidimensional space by calculating all those partial derivatives at once, we simplify it. We pick just one parameter, find the optimal move for that specific coordinate, update it while holding everything else constant, and then cycle through the rest. It is a super efficient way to navigate step by step.
But what if the terrain isn't smooth? Sometimes we hit strict constraints or absolute values that create these jagged, non-differentiable edges where you can't even calculate a standard derivative. For those hazards, we bring out specialized tools. The proximal gradient method helps us step around complex penalty functions. Soft thresholding smoothly shrinks small coefficients to zero when we're near those sharp corners. And projected gradient descent mathematically pulls us back to safety if we accidentally step completely out of bounds.
Let's actually put a couple of these tactics side by side. We talked about coordinate descent handling things one variable at a time to keep calculations simple, but when our data matrices scale up into the millions, we turn to singular value decomposition, or SVD. From an optimization standpoint, SVD takes a massive, unwieldy data matrix and factorizes it into smaller, denser components. It does this by minimizing the lost energy, or residual error, between the original data and the compressed version. This lets our models pull out the most critical predictive features without drowning in the sheer size of the landscape.
So, we've trekked all the way from the basic gradient compass to dodging the overfitting trap right through to coordinate descent and matrix factorization. But here's a thought I want to leave you with. As these data landscapes grow infinitely larger and more complex, what kind of new mathematical compasses are we going to need to invent to navigate them? Because at the end of the day, optimization is the ultimate bridge between raw data and true predictive power. Keep exploring that space, and thanks so much for joining me on this explainer.